look at some differential equations. So this is not the first day of the differential equation, and what I want you to do is I want you to solve for y for each one of the cases, in terms of x, of course. All right, I'm going to give you a little bit of time first. Yes, how about the first one? So I'm sure you've already thought about it. In case of the first one, I'm sure you can easily do this one by having dy over dx equals y. And then through the separable differential equations, you would have seen that, hey, in this case, y should be equal to e to the x, or c times e to the x, I guess, constant. So you could have done that. All right. How about the second one? Yes, you're thinking about it a little bit, I'm sure, and you can maybe insightfully think that, hey, y could have been either e to the x, because when you take the derivative of e to the x twice, they'll still be equal to each other. So to generalize this one, I can multiply that by c. Or you could even say that, hey, y could have been equal to c times e to the negative x. But the question is, what if we don't have that insight? What if somehow you're looking for a more systematic way of doing it? How would you be able to do it? Then we'll be a little bit in trouble. How about the third one? I mean, all I have done was just add up these two things together, kind of a little bit here, but now it became very difficult. How do you do it? We're going to come back to this question later. Now, so today, what we like to do is, how do you solve second order meaning this one, second order differential equations. All right, now let's look at this example first. So when you look at the second order, we call this one as a linear differential equations. But when you set this second order differential equation is set to equal to 0, then we know this one, we call this one as a homogeneous differential equation. And we're going to be looking into that for now. And we're going to be looking at non-homogeneous differential equations later. So when you examine this example, y double prime minus y prime minus 2y has to be equal to 0. How do you do this? Yeah, meaning the original function y, when you take the derivative and the second derivative, somehow all be cancelled away with this original function, or 2 times of the original function. I don't see any other x's here. Only thing that I see is some sort of constant and canceled away with this one. So you gotta be thinking, what could it be? I mean, I'm thinking one possible way would have been y could have been the function that e to the rx. The reason why I'm setting this one up as possible solution is because when I take the derivative of y, the coefficient of x, we call that as r, coefficient of x will continually just come out as a coefficient of the entire expression, and then hopefully it will cancel away these things. Now, of course, c can be in the front as a general constant, but for now we're gonna just think about, we're not gonna think about that at this point, we're just gonna think about that a bit later. So then, wait a minute, what could be possible? All right, let's assume that y is supposed to be this one, and then since c is common all throughout, I'm just gonna factor c out here. So if y were to be a function in terms of y e to the rx power, then what is y prime? Oh, that's r e to the rx. What's the y double prime? Oh, that's r square e to the rx. So in fact, using these three, what we end up getting is you can rewrite the original equation, y double prime. So we have r square e to the rx minus y prime, which is r e to the rx, minus 2 times of y, which is e to the Rx has to be equal to 0. Then in that case, what I can do is I can factor out e to the Rx. And then we have r squared minus r minus 2 equal to 0. And then you can see that this kind of resembles our original homogeneous differential equation. And in fact, as you can see, this will exponential part will never be equal to 0. So this quadratic equation will be the only one that will give us the important information about r. And we call this one as characteristic equation. So by looking at it, you can see that characteristic equations is very similar to what you see over here. Then when in this case, you can set r squared minus r minus 2 equal to 0. Then you can easily see that r minus 2, r plus 1 equal to 0. Then r should be 2 or negative 1. In other words, when r equals 2 or negative 1, this becomes our solution for this differential equation. So for example, we have two different cases. One such case would be r, y sub 1, first case would have been equal to c sub 1, since this is first case, e to the 2x. Second case would have been c sub 2, e to the negative 1x. We have these two as the answer. Both of them, or either one of them, will make this one equal to 0. Now, but the thing is then what is y? Since both of them is equal to 0, our y will be equal to c sub 1 e to the 2x plus c sub 2 e to the negative x. Both of them together will be our complete answer. Because if you think about it, when they're linearly independent, when they're independent to each other, when I combine them together, it will still be equal to 0 anyway. So that's basically what I can do. So if I were to generalize this one, then what if I have general second degree homogeneous differential equation? Then what would you do? Yes, we're going to do it exactly the same way as before. If you assume that y is equal to c e to the rx, where I'm assuming the a, b, and c are the constants, then you can say y, and then I'm going to factor c out. So y must be equal to e to the rx. Y prime must be equal to e to the rx times e times r. Y double prime is equal to e to the rx times r squared. So by putting them in, our equation is a r squared e to the rx plus b r e to the rx plus c e to the rx equal to 0. So when you factor out e to the rx, guess what? We get a r squared plus br plus c equal to 0. And here you can see that we call this one as a characteristic equation. Alrighty. And then of course r will be, in this case, when you solve it, would be negative b plus or minus square root of b squared minus 4ac all over 2a. You know, quadratic formula. Generally, that would be the solution for the r. But so what I have done was I prepared three equations here, three examples, and then I want you to look at them together and see what we end up getting. So for the first one, this is our case. Y double prime plus 2y prime, and then minus 3y is equal to 0, and then I want you to solve this equation. How would you do it? As soon as you look at it, you get to realize that your characteristic equation can be easily be seen as r squared plus 2r minus 3 equal to 0. Then you know that you can factor this one, r plus 3, r minus 1 equal to 0. Hence, r will be equal to negative 3 and then 1. What does that mean? That implies that your y should be equal to c sub 1 e to the negative 3x plus c sub 2 e to the x. So we have these two things combined together will be our general solution. If c sub 1 is equal to 0, then only this will be surviving. If c sub 2 is equal to 0, then only this will be surviving. If both of them are equal to 0, y could technically be equal to 0 as well, right? And then 0 is equal to 0. So this will be the general form of our solution. Alrighty. Now, so we didn't have any much problem here for the first case. How about the second case? Alrighty. So I'm going to go to the characteristic equations right away. And you can see that r squared plus 2r plus 3 equal to 0. Now, when you compare these two, it looks very similar except the last number. And either using the quadratic formula or completing the square, I'm sure you can easily see that r should be equal to -1. And then this one comes from the plus or minus I radical 2. So what I'm thinking about from here to here is I was looking at r plus 1 squared plus 2 equal to 0, and then from there I couldn't come to here right away. All right, then yes, my answers will be y is equal to c sub 1 e to the -1 plus I radical 2 x plus c sub 2 e to the -1 minus I radical 2 x. So then when you look into this one, I think first part you don't have that much issue, as in I can bring the x's out. So we get c sub 1 e to the x, or negative x rather. In fact, e to the negative x is common, so what I can do is, let me factor that out. E to the negative x is common. So we have c sub 1 e to the I radical 2x plus c sub 2 e to the negative I square root of x. Oops, square root of 2x. But even though that this is the answer, but some of you may feel that, hey, I have exponent with complex number. You may not feel comfortable about that. Is there another way for us to describe this one? Yes, there is. In fact, if you remember, I'm going back to cosine I sine. So if you remember, e to the theta I. What is e to the theta I? That was equal to cosine of theta plus I sine theta. You were able to see the complex number in this format. So we used to call it CIS, cis, or polar form of complex number, trig form of complex number. So this was the one idea which we talked about it earlier in your previous classes. So if I want to use this, then what I'm end up getting is this. E to the radical 2 xi now becomes cosine of radical 2x plus I sine of radical 2x. And then of course when I have negative e to the -2 or negative radical 2x I then means cosine of negative radical 2x plus I sine of negative radical 2x. Now, but one thing is you have to realize that cosine is an even function, so this one is equal to cosine of radical 2x. But sine is an odd function, so negative sign will come to the front, negative I sine of radical 2x. So in fact, one with the negative in the exponent will make the sign negative, but cosine is the same. So if I were to rewrite this, so I'm going to put this one away a little bit. If I were to rewrite this one, it's going to be a little bit longer, but it's okay. E to the negative x c sub 1 cosine of radical 2x plus c sub 1 I sine of radical 2x. So we're okay with that one. On the other hand, second one, we get plus c sub 2 cosine of radical 2x, because, you know, cosine becomes an even function, so negative sign disappears, minus c sub 2i sine of radical 2x. So in fact, you can combine c sub 1 and c sub 2 in case of cosine, but in case of sine, we need to subtract them with the complex number I. So the way which we can rewrite this one is e to the negative x. When I combine them together, I can rewrite it as c sub 3 cosine of radical 2x, and then plus c sub 4, because I don't know what the number is. C in this case doesn't have to be real all the time. C sub 4 sine of the radical 2x. So that becomes my general solution for this function. Alrighty. So now next one is this. Let's talk about third case. When you look into this one, you can see that our characteristic equation will be r squared plus 2r plus 1 equal to 0. And then that's rather simple, because you can factor this one as r plus 1 squared equal to 0. So you get r equals negative 1. Instead of having two roots, you end up having only one root. Then obviously our answer seems to be y equals c sub 1 e to the negative x would have been one of our answer. But how about the other answer? It cannot be the same thing. Even if I were to call it c sub 2 e to the negative x, it's going to be the same thing as the other one. But one thing about this is that there's a suspicion when it's double root, derivative of y or y prime and all those things will be very similar. So one thing that I can mention is maybe we'll try, let's call this one y sub 1. Maybe we'll try this one, c sub 2x e to the negative x. I mean, c sub 2 is factored out quite easily, so what if I were to assume this one? I'm attaching x to it. When it's a characteristic equation, it's a perfect square. Now let me try to do this one and then verify that if this one is the answer or not. So we're gonna get y sub 2 is equal to x e to the negative x, and y prime of 2 becomes, derivative of x becomes e to the negative x, and then minus derivative of the e to the negative x is negative sign comes to the front, negative x e to the negative x, and y double prime sub 2, derivative of this one becomes negative e to the negative x, and derivative of this one is negation of this, so we get plus x e to the negative x, and then minus e to the negative x. So what I'm going to do is I'm going to double this one and then add up all three. So then negative e to the negative x plus x e to the negative x minus e to the negative x plus 2 times of e to the negative x minus x e to the negative x, and then original plus x e to the negative x. Let's see if this one is in fact equal to 0 or not. Oh, e to the negative x can cancel away these two of them. And then I have 2 of the positive x e to the negative x, cancels out with the 2 of these. So it indeed is my answer. So my answer y would have been equal to c sub 1 e to the negative x, but because it's a double root, my second answer will be c sub 2x e to the negative x. All I have to do is just attach x whenever I have a second root here. It's the same as the first. All right, so these are the 3 cases which we have to think about, and I'll see you later.